Today we are Today, we are delighted to host Dr. Mami Deka. Mami is a postdoctoral researcher at TINAF Astronomical Observatory of Capodimonte, working on stellar pulsation modeling of radial stellar pulsators, especially array and classical Cepheids. Today, she will discuss about a relevant comparison between the MESA and the Stellingwerf codes. Thank you, Mami, for accepting our invitation. The floor is yours.
Julia. Hello, everyone. Good morning. I am Mami Deka. I currently a postdoctoral researcher at the Capodimonte Observatory. First of all, I'd like to thank the organizer for giving me this opportunity to present my work, especially Julia and Fatima. Today, I will discuss about my recent work on modeling classical Cepheids with a particular focus on intercalibrating two pulsation codes, MESA-RSP and the Stellingwerf code, using observation of large mesoneuric cloud Cepheids. The classical Cepheids are radially pulsating variable stars, and they belong to population 1 stars, and their intermediate mass stars, and their mass ranges from 3 to 11 solar masses. And their pulsation mainly driven by Kappa mechanism in their helium ionization zone. And these stars, as standard candles, play a crucial role in measuring cosmic distances. Additionally, they also serve as excellent astrophysical laboratories for testing theories of stellar evolution and pulsation. And they lie in this region of the HR diagram, which is called a classical instability strip. And the core of my research work mainly built upon the pulsation models, built upon the hydrodynamic equation that also incorporates the physics of convection and radiation transfer. These models provides a critical physical link between the observed pulsation properties such as period and amplitude with the intrinsic stellar parameters, for example, mass, radius, luminosity, and effective temperature, also the chemical compositions. And when we improve our understanding of these models, and we not only improve our theoretical understanding, but also we can refine the period luminosity relation. And this refining of this period luminosity is very important in the precision cosmology. And also, we can estimate the period age relation using these models, which is also a very powerful tool for galactic archaeology. And they also could be used as for stellar population analysis. So there are in general two main types of pulsation models. One is linear non-adiabatic pulsation models, and another is non-linear non-adiabatic model. In linear non-adiabatic models, we take the hydrodynamic equations. We take the hydrodynamic equation and we linearize them, but still including the non-adiabatic part, like the energy loss and gain part. And while these models only gives us period and instability strip, but also instability is the age where the start or stop to pulsate. But real stars are very complex, so we need the nonlinear part to capture the full dynamics of their pulsation. And in nonlinear models also gives us period and instability strip, but along with that, we also get the full amplitude light graph, which we can directly compare with observations. So there exists several pulsation code to compute pulsation models. One of the widely used code is the Stellingwerf code, which is still actively maintained and continue to calibrate models with observations. And this plot shows some of the models that compared with observation, both with photometric light curve and radial velocity curves. And this plot shows some recent period luminosity relation that has been obtained from using Stellingwerf code by Julia and collaborators in the LSST bands. And there exists another important code, which is Budapest Florida code. This code also includes a advanced treatment of convection. And Pollard and the collaborators also reported that they could also that double mode RLE stars or pitch Cepheids would then necessarily occur if we include the turbulent convection in our hydrodynamic models. This was challenged by later by Smolek and collaborators, and they suggested that this is due to the omission of the negative buoyancy from the hydrodynamic models. However, these models also have some limitations. That it also includes the convection simplified version of convection treatment, so it also leads to several free parameters which still needs calibration with observations. And there another code is MESA-RSP, which I particularly use for my work. And this stands for Modules for Experimental Stellar Astrophysics. And RSP stands for Radial Stellar Pulsation Code, originally developed by Smolek and collaborators, but it was later integrated in MESA by Paxton and collaborators in 2019. And it is user-friendly and publicly accessible for researchers worldwide. So it gives the researcher to work in a single platform for both evolutionary and pulsation models. But this code also has the same limitation as other 1D code. It also requires calibration of these free parameters due to approximations in handling turbulent convections. And this could be possible with if we calibrate this parameter with observational data. So the calibration part, for the calibration, COVAX and collaborator has led a important effort, which for RRB and RRC stars. Here we can see that they have found a very good fitting for radial velocity curve, both their code, Budapest Florida code and RSP code. But if we look into the light curve, we can see the matching of the light curves with observation still remains challenging because because there are some other uncertainties along with the turbulent convection period. There are atmospheric modeling which we need to consider when we convert our luminosity model luminosity into the passband required passbands which needed atmospheric models. So there are still lots of work needs to be done in this regard. So this is, but yeah, I also want to note that if we use MESA for mean results like mean period and mean period luminosity relation, it doesn't show much discrepancies with observation. This is an example of my recent work where we have used this MESA code to estimate the instability strip age in the instead of first classical Cepheids. And we could see that it has showed very good agreement with previous work for both observations as well as theoretical part. And then we have also compared our instability strip age for classic type 2 Cepheids with that of classical type 2 Cepheids generated with RSP with that generated with Stellingwerf code. Here also you can see very good consistency. Whatever difference we could see is because of the differences in the adopted metallicity values. So for BL Hersters, Sushmita Das and her collaborators produced a extensive grid of fine grid of pulsation models. BL Herstar is a subclass of type 2 Cepheids. And here also we can see that the mean period luminosity and period Wasson-H relations is aligns very closely with the empirical relations. However, they have also found that if we look into the detailed light curve, we still need calibration of this parameter to have a complete consistency with observational light curve. And this becomes more clear when we move to the Fourier parameter space or multi-phased light curve as well as other empirical relations. So in this regard, we have led one effort to calibrate this parameter for classical Cepheids. As there are, for this case, we have chosen 18 LMC Cepheids, which has been already well modeled by Stellingwerf. Why we choose this Cepheids? Because there remains several unknown free parameters. For example, the main input parameters are mass, luminosity, temperature, and chemical composition. And then there are other turbulent convection parameter. In MESA, there are 8 such parameters. So it will increase the number of unknowns, which will make the process very difficult. So once we have well-modeled observation, then we already constrain this parameter mass, luminosity, temperature, and chemical composition. So now we are left with this convection parameters, and this reduces the number of unknowns and also make this calibration process a bit easier. So this is the results of our modeling. When we just use the convection parameter as it is in MESA, so we could see that most of the stars has a good light curve shape with observation, but we can see some mismatch in terms of amplitudes. Yeah, although we could see some only few of the stars show very different light curve structure than the observations one. So once we calibrate this parameter, turbulent convection parameter, we could see in the left panel they have like very good match. Here we have only for this work we only calibrated 2 parameters, mixing length parameter and the eddy viscosity parameters. And in the right panel we have shown the model comparison between Stellingwerf and RSP code, and we could find a very good agreement between these two models. And for one star, we had to compute hundreds of models. And how did we use this chi-square criteria to find out the best fit models. And this criteria we have adopted from the previous work of Marcella Marconi, but with a bit of a new addition in the optimization technique. This the advantage of this technique is that it gives us individual distance modulus, reddening, and the reddening, which is independent of any scaling relation, and also we get the phase shift between the model and observed light curves. So from this work, we have find that no single parameter set, no single turbulent parameter set could produce all the Cepheids across the entire instability strip. Even when we restrict ourselves within the central region of the instability strip, we could not find a single set of parameters. We have found that different combination of these parameters are needed to reproduce the observations. Then we have, so it suggests that we might, rather than relying on a single parameter set, it will be more efficient to have some empirical relation or semi-empirical relation between these parameters with the intrinsic.
Just a moment, Mami, I can hear you. It's totally my problem. Sorry.
Yeah, can anyone?
Okay, now I can hear you. Okay.
Now, yes, now it's okay.
Okay. So, sorry. So yeah, so this might be due to the case also, like we can.
I think we cannot hear you again.
Yeah.
Am I audible now?
Okay, now we can hear you. Yeah.
So for RLD stars, for works and collaborators, they found a very tight relation between effective temperature and eddy viscosity parameter. For that reason, we also tried to see the correlation between these parameters, and you can see here that we have found very subtle relation between we could see very subtle trends in between the effective temperature period and this alpha parameters. But this might be, but before drawing any conclusion on this in this regard, it's maybe because we have a very less sample yet. We might need more large statistics before drawing any conclusions. Also, it might be the case that for Cepheid, the convective envelope is more extended than the RLR stars. So that might be one case for not getting any relation between strict relation between these parameters. So next, we have also looked at the empirical relation, and we found very good agreement with previous work as well as previous work by Ragosta et al. But here we have also for first time reported to mass-luminosity relation for fundamental and first overtone Cepheids. Next, we have also found the multi-wavelength period luminosity relations as well as period baseline relation. These are also in very good agreement with previous work as well as I have not plotted the comparison here, but yeah, I have a table. Maybe I should have. We found a very good relation with the theoretical as well as the observed relations. And this is the same case for the individual distance modulus as well as the radius of the stars. So next we have checked, like, can different combination of parameters could produce the same light curves. So to detect this, we have changed the use two sets in the MESA-RSP. One is set A, that is the simplest one, and set D is the complex one. So indeed, we can say that they could produce the same light curves. So how to break this degeneracy? So then we have looked at the radial velocity curve amplitudes, and we could see that although the same set of parameters could produce the same light curve, but indeed the radial velocity curve amplitude is different in this regard, because when we change, for example, when we change eddy viscosity parameter, it doesn't much affect the temperature contrast in the models, but it definitely decrease the dynamic motion of the envelope. So accordingly, when we increase the eddy viscosity parameter, it reduces the amplitude of the radial velocity curve. But this is not true for all bands, because for V-band, optical V-band, and the bluer bands, they are more sensitive to temperature. So we might see this effect in this bands. But when we consider the K band, it's more sensitive to the change in radius. So the K band data might not be entirely independent from this radial velocity data. And so next. Another conclusion is that if the star has an effective temperature more than 6,000 Kelvin, then it prefers the simplest convection theory. But if we have some stars with an effective temperature lesser than 6,000 Kelvin, it might be more efficient to consider this complex convection theory, which includes the effect of turbulent pressure, flux, in some cases radiative loss as well. So based on the previous work, the results we have found, we have now extended our grid by including very fine steps in mass, metallicity, luminosity, and helium content, as well as effective temperature. And we have started generating the model light curves in the synthetic light curves in the LSST bands as well. And in future we will apply the same model fitting techniques here to derive fundamental stellar parameters for a wide range of classical pulsators. And this synthetic light curves also could be used as template for rapid classification and parameter inference from the large amount of data expected from LSST. And the model fitting technique will give us stellar parameters, reddenings, individual reddenings, and distances, which could be used for precision distance measurement, as well as for galactic archaeological applications. Most importantly, we envision a feedback loop process here. We will use this model to infer the stellar parameter from observations. But if we found a significant mismatch between observation and models, then we will use those input to improve our models. Now, this is my last slide. Now, how WST could be helping in this in constraining these parameters, as well as in the advancement of pulsation models. So, WST will provide us chemical compositions for a very large statistical samples, and we have seen that chemical composition is a very fundamental parameters in the models. And also to estimate the stellar fundamental parameters, we need radial velocity curves along with the observed light curves to put tighter constraints on these parameters. And this could be and we will get a very huge number of expect a very huge number of radial velocity from WST. And next is now we are comparing the model light curves with observed light curve by converting our bolometric light curves into some particular pass bands. And this includes uncertainties, because the atmospheric models are also based on turbulent convection, but it is also based on various assumptions. But if we have time series spectroscopic data, then we could directly compare the temperature curves with that of models. And this will be more direct comparison between model and observation. So spectroscopy and photometric data together will be more like a spectroscopic time series and photometric time series. They will put more tighter constraints in our model computation, as well as for the parameter inference process. So that's it. Thank you.
Thank you, Mami, for sharing your work with us. It's now time for questions and answers. Go. Avram? Ah, no. They're not questions. Okay, Zenek, go ahead.
Yeah, hi. Thank you, Mami, for a very nice talk and summary of your results. I have a question on you were talking about classical Cepheids and fundamental mode Earl stars, and on the sort of a lower temperature regime around 5 to 6.5 thousand Kelvin. I'm now thinking, would there be helpful to have spectroscopic time series for first overtone Earl stars with temperatures around 7 to up to 8,000 Kelvin? Would that be helpful for your constraints on the convection?
That like for RLD overtone stars, it's like very smooth. We might get a very smooth temperature curve. So I'm not sure like it will be helpful for directly comparing with to calibrate these turbulent convection parameters or not. But for Cepheids, yeah, it was.
Okay. Would it be like if you would model a first overtone Earl star,
Yes.
would the model perform either the Florida Budapest code or the Stellingwerf code that you're using? Would it perform better, for example, than for the fundamental mode Earl stars? Is the match better?
Yeah, maybe because there will be less secondary features in the first overtone light
Okay.
curve as compared to
Okay.
the fundamental mode one. Yes.
I see. Good. Thank you. Thank you.
I think that it would be good, for sure, good to have a first overtone RLR, but we also need to increase the observative sample about first overtone mode pulsators. That for now is not so big.
That's all I need to hear. Thank you.
Mami, just a question about one of your first slides showing the presentation of models, no? About nonlinear and linear. Can you go to these slides? I think 3, 4. when you talk about linear and nonlinear models? Mhm. Yes. No. Later on. Oh, okay. This one. No. First, this one.
Yeah.
Here, do you mean in general or with the MESA code? Because when you talk about linear non-adiabatic models,
Mhm.
are you not referring to convection, no? So I don't understand. It's not correct for me, stability strip ages.
Yeah, this is for MESA code. I think
Okay.
it's not true for Stellingwerf code because they are,
Okay, because the treatment of convection is different. In which way
yes,
you
yes,
can obtain red age in this case?
yes, that's true. Thank you for.
No, I mean, so with the MESA code you can obtain red age also in the linear non-adiabatic models.
Yes, yeah, we could because the turbulent convection is already included in the linear analysis as well.
Okay. So the treatment of convection is completely different from the mixed length theory.
Yes,
Okay,
not completely, but yeah, a bit.
a bit, okay. We can speak at the office about this.
Yeah.
Thank you. Other questions? Okay, maybe we can stop here. Thank you, Mami, again for your time and sharing your work. And have a good day, everyone. And see you next session.
Thank
Bye.
you.
Bye.
Bye.
Bye bye.